This video is sponsored by Blinkist. Hello and welcome to this episode of Night Sky News for July 2023 with me, astrophysicist Dr. Becky Smethurst. This is a show where we chat about what you should look out for in the night sky in the next few weeks, and then we chat about what's been happening in space news in the past few weeks. This episode, we're celebrating 1 year of JWST science as it spots the most distant growing supermassive black hole ever found, and we chat about the first image of the Milky Way taken by a neutrino telescope. In this video, I'm not going to be chatting about this piece of research that came out with a new estimate on the age of the universe at a whopping 26.7 billion years old rather than 13.8 billion years old, which is claimed to explain JWST data better. That's going to be its own whole video that's going to come out on my channel next week, so make sure you subscribe so you don't miss out on that. For this video though, there's chapter markers down here if you want to skip ahead to any specific news story, plus any scientific research papers I mentioned are all going to be linked in the video description down below. So without any further ado, let's kick things off and start by looking up. All right, we're kicking things off with a conjunction of Mercury and Venus on the 26th of July, where the two planets will come close together on the sky from our perspective in the west just after sunset. They'll pass just 5 degrees apart, which is less than the width of the palm of your hand held out at arm's length, which means that if you have binoculars and you break them out, then you'll be able to see them both at the same time in your binoculars field of view. Now, unfortunately, not all of us are going to be able to see this. Those of us up here in the north, the sky is just too bright for too long at the minute in the middle of summer, and so by the time it gets dark enough, they're just going to be too low on the horizon, maybe even below the horizon for some of us as well. But if you're between the Tropic of Cancer and the equator, you're going to have the best view, as they'll appear higher above the horizon, making it easier to spot. Plus, if you're in the southern hemisphere, you have really dark skies at the minute because it's in the middle of your winter, making fainter Mercury much easier to spot next to the much brighter Venus. You can watch these two planets getting closer together then further apart again over the next week or so, and keep an eye out for reddish Mars just above them. We'll actually be losing bright Venus from our skies for just a little while as Venus passes in between the sun and the Earth. But it'll sweep around pretty quick and be back in the morning sky by the end of August. Now, the rest of July and August is all about meteor showers. So this is when the Earth passes through the little clouds of debris left behind, usually by comets on their orbits around the sun, and those tiny little bits of debris burn up in the Earth's atmosphere and streak across the sky as shooting stars. And the first one to note is the Delta Aquarids meteor shower, which runs from around about the 12th of July to the 23rd of August, with the peak on the 29th of July. And in previous years on the peak, the Delta Aquarids has given us around about 20 meteors per hour in the darkest of skies. So pretty good meteor rates, around about like 1 meteor every 3 minutes or so. But this year, the 29th of July also coincides with an almost full moon, which also happens to be a supermoon as well, where the moon is closer in its oval-shaped orbit to us, and so it appears much brighter in the sky. So the Delta Aquarids, not likely to put on a good show this year because of the moon, but all hope is not lost because the Persieds Meteor Shower also runs from the 17th of July through August and is one of the best meteor showers in a year. It's my favorite anyway, because in dark skies it produces 60 meteors an hour. That's like 1 meteor every single minute. Now, the peak of this meteor shower this year is the weekend of Saturday the 12th of August to Sunday the 13th of August. Plus, the moon by that time is just a thin sliver of a crescent and only rises in the early morning sky, making it extra dark for meteor spotting in the evening sky. So where do you want to look if you want to spot some meteors? Well, all the meteors will appear to be coming from what's known as the radiant, which for the Perseid meteor shower is in the constellation of Perseus. That's how it gets its name. So if you're in the northern hemisphere, that's in the northeast. So the best thing to do is to look in the exact opposite direction of the southwest. So think about like where in your garden is sort of the last place to get the sun, or what room in your house is the last to get the sun before the sun sets in an evening, and face that direction and then just lie down and look directly upwards and you'll see the meteors streaking out overhead. If you're in the southern hemisphere though, as you get further south, Perseids drop stops just below the northern horizon, and all the meteors will be streaking up from there. So you want to sit facing north to see those that actually shoot above your horizon, which means you'll probably only be able to see half of the meteors in the meteor shower, so 30 meteors per hour or so. So one of the reasons why I love to watch a meteor shower with a group of friends or family, because you can all keep an eye out on different parts of the sky so that you don't miss any. Plus, what I love about the Persieds this year is that it is on a weekend. And so I think many people might be planning, you know, a weekend trip away, or might be on holiday already, perhaps to somewhere with a dark sky, you know, on a beach, on an island maybe, or even just to like a national park to hike or to camp. But remember, these wilderness places that are remote are also away from light pollution. So if you are planning a trip, don't miss out on the night sky as well. Make sure you make the most of it. While you're there and looking up, see if you can spot the summer triangle as well, if you're in the northern hemisphere anyway. It's not a constellation, it's just 3 very bright stars that make a large triangle across the sky. You've got Vega, Altair, and Deneb, and it'll be directly overhead around midnight through the end of July and the beginning of August. Plus, they frame the Milky Way nicely, allowing you to spot it running across the sky if you're somewhere dark. All right, that's enough of looking up at the night sky, but before we come back down to Earth to chat about space news, I want to say a big thank you to this week's video sponsor, Blinkist. The Blinkist app allows you to understand the most important points from over 5,500 non-fiction books and podcasts in just 15 minutes. I don't know about anybody else, but I wish that I had more time to read, especially non-fiction, so that I can learn something new and consider new perspectives. With Blinkist's bite-sized summaries, I can engage with the book and fit it in around just everyday life, reading on my commute, listening on a run, or even while doing chores. I often use it to work out if I do want to then read the whole book, sort of like an extended blurb, if you will. And I did this with Julie Smith's Why Has Nobody Told Me This Before, which has advice for day-to-day management of your mental health and any anxiety from a clinical psychologist. Blinkist also allows you to suggest books that don't have summaries yet, and also create a space with friends or family where you can share recommendations. So if you want to check out Blinkist, you can get a 7-day free trial plus 25% off their annual premium with my link that's in the video description down below. So thank you so much to Blinkist for sponsoring this video. And now let's chat about what's been happening in space news in the past month. All right, so this month's big news was the evidence for huge light-year-long gravitational waves detected using pulsar timing arrays, essentially making a galaxy-sized telescope using dead stars. I made lots of shorts on this, including how this was only possible now thanks to the Juno mission to Jupiter. And of course, I made a long video that went into all of the details and how we could now use this method to study the first few seconds of the universe's life for the first time, and maybe get at some new physics. So check that out if you've not watched it yet. Here though, let's chat about JWST, because it has been an entire year since we first laid eyes on those first 5 science images that were released by NASA and ESA on the 12th of July, 2022. If you remember, I was at the UK National Astronomy meeting with over 600 of my fellow astrophysics colleagues, and I recorded my live reaction to the images getting released with them, and then also an explainer of each image as well. Now, to celebrate that 1-year milestone, NASA has released another stunning image. This time of the Rho Ophiuci cloud complex, a nebula where new stars are forming just 390 light years away, the closest star forming region to Earth. Now, the darkest areas are where dust and gas is thickest. It's shrouding the new stars that are forming, whereas the existing stars have already blown all of that gas and dust away. Now, as always with JWST images, this is infrared light that's been detected. Infrared is light that we cannot see with our eyes. So the color you're seeing in this image is a false color. However, it's been colored so that your eyes can pass the scientific information that's there. The blues is where we're getting shorter wavelengths of light from much hotter regions in the nebula, whereas anything colored red is where we're detecting longer wavelengths of light, which is where the cooler regions of the nebula are. So that was spectacular to see, but I don't think it was the most spectacular image that we got from JWST this month, because we finally got an image of my favorite planet, Saturn. Meaning we also now have JWST images of all of the gas giants. Now, I actually made a short on how we actually managed to do this with JWST, since the planets are so incredibly bright and JWST is so sensitive, if you want to check that out. But back to this amazing image of Saturn. Saturn itself is pretty dark in this image because there's lots of methane in its atmosphere, which we know absorbs the sun's infrared light rather than reflecting it back so we can see it. Unlike the ice and bits of rock in the rings, which do reflect a lot of infrared light, meaning that the rings properly shine in this image. You can also easily spot 3 of Saturn's moons in the image, which was one of the main science goals of this JWST project, to study Saturn. You know, JWST, with its incredible sensitivity, should be able to spot any of Saturn's moons that were missed, either with ground-based telescopes or even by the Cassini mission that was in orbit around Saturn for many, many years. And finding all of Saturn's moons essentially helps us to piece together the history of the Saturn system. Now, there's no scientific research paper that's actually come with this image yet. The team have got a lot more images and also many spectra to analyze, which I imagine is going to take some time because it's brand new data that they've never worked with before. You know, it's probably throwing them some curveballs in there. So eventually we will get a scientific research study on this, and I'm really excited for when that does come out, obviously, and I'll cover it on my channel when that happens. Now, from the backyard of our solar system to the most distant galaxies in the entire universe with the JWST CEERS survey. A team who are using JWST to take deep images of a large area of sky to find the most distant galaxies, sort of like a much larger version of the Hubble Ultra Deep Field, but with JWST. Now, the data was released back in January, which we chatted about in my Night Sky News video then, and now a load of science research papers have been published analyzing all those images, which I'll link below if you want to dive in. I'll talk about one of them in a minute, which claims to have found the most distant growing supermassive black hole in the universe. While we're talking about pretty JWST images, I couldn't not talk about this incredible data visualization that's been produced by the CEERS team. They've taken a 2D image and worked out the distances to all the galaxies in it, and then made this 3D map of this area of the distant universe, zooming into the galaxy with the greatest of distances that they found, now dubbed Maisie's galaxy, after it was found on the 9th birthday of Maisie Finkelstein, the daughter of one of the CEERS team members, Steve Finkelstein, who leads this research study that's been published on its discovery. Now, the distance that they've calculated to this galaxy has been done solely with the images that they have, which is a much less precise way of getting at the distance of galaxies compared to taking a spectrum, where you split the light through a prism and you get a trace of how much light at each wavelength you receive. And what you're looking for when you do that is a drop off in the amount of light, which is caused by intervening hydrogen in the universe absorbing light from that distant galaxy as it travels to us at a very specific wavelength. But the thing is, the light from that distant galaxy is also stretched to longer wavelengths by the expansion of the universe. So you're constantly losing that wavelength as it's stretched to that, and end up with a very sharp drop off. So then if you can work out, okay, what wavelength do I detect the drop off at, and then compare it to the wavelength that you know that hydrogen absorbs at, you can work out how much the light has been stretched by to longer wavelengths. Red shifted is what we call it, which is denoted by the letter Z. Once you know that, you then know how long the light has been traveling through the universe for, and therefore how distant that galaxy was. Pinpointing that drop-off is very easy if you do have a spectrum, but it's much less precise with images that let in big ranges of wavelengths. But if that's the only data you've got, then that's the data that you work with, which is exactly what Finkelstein and collaborators have done here. They got an estimate for the redshift of 11.8 plus 0.3 minus 0.2 uncertainty, meaning we're seeing that galaxy as it was when the universe was just 370 million years old. That's very early in the universe's history. Now, because this distance has only been derived using images alone and not with a spectra, it is just a candidate, very distant galaxy. Now, the spectrum could actually reveal that it is much closer, and that drop-off is due to something else. Until then, though, it's just yet another galaxy on the pile of candidates for the most distant galaxy found by JWST yet, or at least so far. But I think what's interesting is that its existence that early in the universe's lifetime will help us to constrain our models of how galaxies formed in the early universe and how fast they formed their stars. Again, something that I'm going to be talking about more in next week's video when we chat about this new study using these very distant JWST galaxies to claim that the universe could be almost twice as old as we think it is. But Maisie's galaxy is not all they found in the CEERS data. So this research study from Larson and collaborators was also released this month, claiming to have found the most distant galaxy with a growing supermassive black hole in its center, what's known as an active galactic nuclei, an AGN, or a quasar. Now, this is only at a redshift of 8.7-ish, meaning that we're seeing this galaxy when the universe was just 570 million years old, about 200 million years later than Maisie's galaxy that we just saw. But this still is a really big deal, at least if it is indeed a growing supermassive black hole, but we'll get to that in a minute. And the reason why it's such a big deal is because one of the big open questions in astrophysics is when and how do the first supermassive black holes, or black holes in general, form in the universe? So we see supermassive black holes in the centers of galaxies in the nearby universe that are billions to tens of billions of times more massive than the sun. And we see supermassive black holes at the centers of galaxies when the universe was just 700 million years old that are, again, billions of times more massive than the sun. The problem is the only process that we know of that can create a black hole is a supernova, when the core of a dead star collapses down until it's so dense that light can't escape. To do that, they would have had to grow faster than the physical limit at which a black hole can grow by. So people have speculated that, well, maybe there's another way to make a black hole. Perhaps in the very early universe that is much denser, you can actually take just a cloud of gas and somehow stop it from forming stars and instead just collapse it straight down into a black hole that's maybe 10,000 times the mass of the sun, and you give black holes a little bit of a head start to reaching the supermassive status at around 1 billion times the mass of the sun. And we do have some evidence from the Hubble Space Telescope of gas clouds that could be doing this collapse rather than forming stars. But ideally what we do is find supermassive black holes in very distant galaxies and track their growth over time as we look further and further back to more distant galaxies that we're seeing when the universe was much younger, to be able to crack this problem. Obviously, with previous generations of telescopes, we've not been able to do that. We haven't had the sensitivity to detect these things, but now we've got JWST, we're hoping that we can. So hopefully this plot puts that into context. The blue region here is the black holes that we found before with other telescopes. They're around about 1 billion times the mass of the sun, and we see them back to about 700 million years into the universe's lifetime. The more massive the black hole, the brighter the material that's orbiting around it becomes, and so that makes it much easier to spot. So it's not unreasonable that we've spotted the more massive black holes in the early universe with previous telescopes that weren't as sensitive. But with JWST, we've now been able to find this galaxy at 570 million years into the universe's life, with a supermassive black hole at the center of just 10 million times the mass of the sun. So found at greater distance and lower mass than ever seen before because of JWST, possibly opening the door to finding more of these things and being able to tackle this problem of supermassive black hole growth with JWST. So that's why this result is such a big deal. If this galaxy is indeed hosting a growing supermassive black hole, because the evidence that Larson and collaborators have comes from the spectrum of this galaxy. Again, where you split the light to make the graph of how much light of each wavelength you get. Now, in those spectrum, you see these huge spikes at certain wavelengths that come from gas molecules in the universe giving out that light. To do that, they need an energy source nearby, whether that's the UV radiation from newly formed stars, or whether it's light from the material spiraling around a growing supermassive black hole, because as that material spirals around the black hole, it gets accelerated to huge speeds, it heats up and it starts to glow, usually in things like X-rays, which again can be the energy source that then impacts with electrons that are orbiting atoms out there in the universe. The electrons absorb that energy and they use it to jump up to the next orbit that they could orbit around the atom. But because they're not supposed to be there, they then drop back down and give out the energy they absorbed as light. And because those orbits are always separated by the same amount of energy, the same amount of energy is always given out, which means it's the same color or wavelength of light that is unique to that atom or molecule. So when we look at these galaxy spectra, we see these huge spikes that we can attribute to hydrogen or to oxygen that is glowing. When the gas that's giving out that light though is moving, those spikes get smeared out, because what happens is as the gas moves towards you or moves away from you as it's giving out that light, the wavelength of light gets Doppler shifted. So just like when an ambulance races past you and you hear the sound that the ambulance is giving out get squashed to a higher pitch as it comes towards you and then stretched out to a lower pitch as it moves away from you, the same thing can happen to light as it moves towards and away from you. It gets squished to a shorter wavelength and stretched out to a longer wavelength. So if you plot that on a graph of wavelength on the x-axis, instead of a big spike, it is smeared out as some of the light moves towards you and therefore gets squished to a shorter wavelength, and some of it moves away from you and gets stretched to a longer wavelength. And that can happen if you've got newly formed stars that are throwing off a load of material, or that dust and gas that you see in nebulas is getting thrown off away from them, and so therefore the gas is moving. But it can also happen if you've got gas spiraling around a supermassive black hole as well, a growing supermassive black hole. Now, the faster the speed of that gas, the more that spike is smeared and broadened out. And we see this for growing supermassive black holes in galaxies in the nearby universe, that they have these huge broad features and also the narrow spikes from star formation in their spectra. So when Larson and collaborators fit models to their spectra of the distant galaxies in the CEERS JWST data, they found that for this galaxy, it was best fit by two components: a spike and a broadened component shown in the green there, and not a single spike shown in either the blue or the purple. The lower the BIC number here, the better the fits. So because they found a very broad feature, we usually associate, higher velocities with supermassive black holes rather than stars, they assumed this must therefore be a growing supermassive black hole in the early universe. And of course, also the amount that the emission line that you're seeing is broadened by tells you how fast the gas is moving, and how fast the gas is moving tells you how big the thing is that it's moving around. So they could also use this to estimate the mass of the black hole at 10 million times the mass of the sun, and worked out using that mass that yes, the universe has been around long enough for the black hole to have grown to that mass if it started at the mass of around 10,000 times the mass of the sun of a direct collapsed black hole. Which is great, right? But the problem is, and I think we've seen this multiple times with JWST observations, that we can't just assume that what we see in the nearby universe is going to be the same in the very distant universe, which I've talked about a few times in videos on this channel already. That broad feature might not be from a growing supermassive black hole. It could be that those extreme velocities are reached because you have extreme star formation happening in the very early universe in this galaxy that is throwing out these stellar winds, throwing off all that dust and gas in the nebula that you see at much higher velocities than we see today in the Milky Way. And Larson and collaborators even state that they cannot rule out that what they're seeing is due to stellar activity rather than black hole activity. So while this result is really cool and exciting, and I really do hope that it is a growing supermassive black hole, I think we just need to learn a lot more about the early universe with JWST first. Finally, let's chat about IceCube and the first ever image of the Milky Way taken with neutrinos. A result that was a little bit lost and forgotten because it was announced on the same day as the big gravitational wave discovery, but it is a really cool result. It is the first time that we've seen the Milky Way with a particle as opposed to in a different wavelength of light. So I guess we better start with what is a neutrino. They are absolutely tiny fundamental particles that are produced when either an atom breaks apart, like in radioactivity, or atoms are fused together, like what powers the sun and all of the stars. They are actually the most abundant particle in the entire universe. And a fun fact that I learned from Clara Nellis, who is a particle physicist at CERN, is that if you hold your thumb up, then there are 1 billion neutrinos per second passing through your thumbnail. Which is insane, right? But they barely react with matter, so you just don't know that they're there. So where are all these neutrinos coming from? Well, the sun, for one, as we just heard, but also due to something called cosmic rays. Now, these are incredibly high energy particles, usually protons, that make up the nucleuses of atoms, that are accelerated to huge speeds by some unknown process. And when they hit the top of the Earth's atmosphere, they produce a cascade of particles, including lots of neutrinos. But that kind of particle cascade can also happen if one of these cosmic rays happens to hit the gas between stars, like in nebulae, and then those neutrinos that are formed in that cascade can also reach Earth as well. Now, the problem is, we still don't know what produces a lot of the high energy cosmic rays. We know that some of them come from supernova when a star dies, but that can't account for them all. So pinpointing the location of these cosmic rays and where they're coming from would be extremely helpful to figure out what's making them. The problem is, as they hit the top of the Earth's atmosphere and produce that cascade of particles, all of that information on their direction, their location is lost. So ideally what you do is detect the neutrinos that are coming from the cascades that happen, just where the cosmic rays were produced when they impact with all of that interstellar gas. But how do you detect neutrinos when they barely interact with matter? Well, what the IceCube team did was bury a detector under several kilometers of ice in Antarctica to filter out every other kind of particle. Then when just 1 neutrino of the billions that are passing through happens to interact with a frozen water molecule, then it creates an electron that is traveling faster than light can in ice. This creates a sort of sonic boom of light that's known as Cherenkov radiation, light essentially that IceCube can then detect. The hardest part, though, is distinguishing the light that comes from neutrinos that are made in the atmosphere versus neutrinos that are coming from the sort of interstellar gas. But a combination of energies, the direction that you detect things from, and then also whether you detect another type of particle called a muon from that cascade in the atmosphere at the same time. And then you can then sort through them and pick out like the 1 neutrino out of the 100 million events that trigger the detector that is from this sort of interstellar neutrino source. So then what the IceCube team did was use machine learning. They trained an algorithm to look for those sources, and then they triangulated the direction that neutrino came from in the sky and found this very blob-like picture of where all the neutrinos are coming from. The darker the color here, the more significant the detection is, and the lower the chance of it being a statistical fluke in the data. The highest significance is what's called 4.5 sigma, which means there's a 1 in 150,000 chance that their detection is actually a fluke. Now, you're probably thinking 2 things here. First of all, that doesn't look anything like the pictures that you saw in the news. Well, the data was made much prettier for the press. It was colored blue and overlaid on a darkened image of the Milky Way, taken with visible light to show the positions of the stars and the dust as well. So you can think of this as more like a data visualization than an actual image. And the second thing you're probably thinking is that these blobs of detections aren't exactly going to tell us much about the origin of cosmic rays that are producing these neutrinos. And you'd be right. We can't actually pinpoint the emission to any of our sort of top suspects with the data that IceCube currently have. But that's because this is just a proof of concept that we can actually do this just in time for IceCube to get an upgrade. IceCube Gen 2 will be 10 times bigger, allowing for more neutrino detections to sharpen up this image and trace back where these neutrinos are actually coming from to hopefully finally crack the problem of what is producing these high energy cosmic rays. All right, that's it for night sky news for this month. As always, if you snap any pictures of the night sky, especially the Persieds Meteor Shower, then I would always love to see them. Plus, if you come across any space news stories on your travels around the internet, send them my way or over on social media, and hopefully I'll explain them in a future video. And remember to keep an eye out for next week's video on that paper claiming the universe is nearly twice as old as we thought. But until next time, everybody, happy stargazing. You can see up to 60 meteors a minute. That's 60 meteors a minute. Oh, if only. That would be a proper meteor shower. We've got Vega, my favorite planet? My favorite planet and Saturn smushed together. Sure. Ooh. Sorry, I'm sitting a lot closer because of the light situation. I just kicked the camera. Oxygen that is glowing. Oh no, my light just ran out of battery. No, what do I do now? Finally got an image of my favorite planet. I did it again. Oh my God. Planet, it's just a thing now. We're just going with it. We're just going with it. It's fine. I can see you grow when you're a black hole. I can see you. Oh, you really start formation. I can see you in the JWST data.